Hey everybody. This is our discussion on Stokes theorem, section 16.8, the second to last section and second to last major topic in chapter 16, our discussion of vector calculus. So we have Stokes theorem in 16.8 and then divergence theorem in 16.9. And let's just start right off with the theorem itself, Stokes theorem. We have a lot of assumptions here, so you can read through them. These are bits that we've talked about in the last couple of sections, things like orientability of a surface and so on. All important details here. For the rest of this lecture, I really won't be super carefully checking all of these details each time we apply Stokes theorem, but all of the things that I say will be under the assumption that the assumptions of Stokes theorem are satisfied. And provided these conditions are satisfied, Stokes theorem says that the line integral of f dot dr is equal to the surface integral of curl f dot ds, where the curve C is the boundary of the surface S. Okay, so a couple notes on this. So I guess maybe kind of a note zero. Why do we care about this? Well, a few different reasons maybe. Sometimes we might want to find one of these integrals, say the left side or the right side, for some particular reason, for some particular application. I might want the surface integral for some reason, or I might want the line integral for some other reason. And it might turn out that computing that integral is very cumbersome. But maybe if we can apply Stokes theorem, the integral on the other side of the equality may be a lot easier to compute. We also get a lot of several nice applications that come directly out of Stokes theorem that we'll see a little bit later on in the lecture, and a lot of other applications that we won't see in the lecture that come up in physics and engineering and so on. So that's why we might be interested in knowing Stokes theorem. Note one down here, what does Stokes theorem kind of say in words? Well, we recall that the line integral of f dot dr, we can think about that as the line integral of f dot t, the unit tangent vector, ds. So this is kind of like the tangential component of the field. And the double integral of the curl of f dot ds, well, we can think of that as the surface integral of curl of f dot n dot normal ds. So it's kind of like the normal component of the curl of the field. So kind of maybe put into words one way, Stokes says something like the line integral of the tangential component of f, the field, over the boundary curve of a surface is equal to the surface integral of the normal component of the curl of f over that surface. So that's maybe one way to think about what Stokes theorem says. Okay, a second note on Stokes. Recall that we discussed some other forms of Green's theorem other than the PDX plus QDY form. And in particular, one of those forms looked like this. It looked like the line integral of f dot dr equals the double integral over some 2D domain of curl of f. And here we kind of said, well, Green's really is a 2D theorem, but if we kind of embed that two-dimensional flat surface in 3 dimensions, we could just think that we now have the ability to have a k vector, a vector pointing up, and we can rephrase Green's as the double integral of curl of f dot k dA. So we can, in a sense, think of Green's theorem as like a special case of Stokes's theorem, where we're only dealing with a flat surface that's in the xy plane. Or we can think of Stokes' theorem as a generalization of Green's theorem, where we take that kind of flat surface in the xy plane and we allow it to be really any surface in 3 dimensions. A third note. So if we have some vector field A, and if we have another vector field F that happens to be the curl of A, So if these two vector fields F and A are related by F equals curl A, that's kind of like vector field F being like the derivative of A. Remember, we had kind of a similar idea where we said if F is grad little f, we call it F a scalar potential. Well, this is, in a sense, the vector equivalent. If F equals curl A for some A, we call A vector potential of F as opposed to a scalar potential, because A's curl is F rather than little f's gradient being field F. Then we can rephrase Stokes' theorem as the surface integral of F dot ds, but F is just curl A, so that's the surface integral of curl A dot ds. But that's just the integral over the boundary curve, A dot dr. So what do we call this surface integral, the surface integral of F dot ds? Well, that's the flux of the field across the surface. So that had maybe a more understandable application or a more understandable meaning than this integral does. So this is just the flux of the field across the surface, provided that we have a vector potential. We see that that flux across the surface depends only on the boundary curve of the surface, not actually on the overall shape of the surface. And related to that idea, even if F is not does not have a vector potential, note that we still have the idea of surface independence for this integral, that the integral over, say, surface S1 curl F dot ds equals the integral over its boundary curve F dot dr. And if I have another surface, any other surface with the same boundary curve, assuming, same orientation and all of those kind of good things, then a second application of Stokes would show that this equals that second surface. So the surface integral over that second surface. So provided two surfaces have the same boundary curve, then the surface integral over their curl is going to be the same regardless of what the surfaces actually are on the interior. And we can also say that if S is a closed surface, that is, if the surface S encloses a volume, there's a little more discussion on that, exactly what that means in the divergence theorem section. Then we can kind of think of S as being, something like a surface that like has a hole in it, and the hole shrinks and shrinks and shrinks. And that hole is bounded by a boundary curve, and that boundary curve is shrinking and shrinking really down to nothing. So if S is a closed surface, we would say that its boundary curve is the empty set. But then the line integral over that boundary curve, we're integrating over no domain. That integral must be 0. So then the surface integral of the curl must be 0 if we have a closed surface. And note the kind of similarity here to the idea of conservative vector fields, where big F equals grad little f. They had the property of path independence, kind of similar to this surface independence idea. And they had the property that a line integral around a closed loop is 0, similar to this idea of this surface integral of the curl over a closed surface always being 0. And as a little aside here, I would like to, this isn't going to be a formal proof, but just as a gut feeling, this statement here kind of seems strange, right? Why is it that if we're taking a surface integral, we don't actually care what the surface is, in a sense, right? It seems like that seems very counterintuitive, if I can select the right thing here. It seems very counterintuitive to say that we're taking a surface integral over a certain surface. We have a field that is a three-dimensional thing. It can be all wonky in all different ways at different points. And yet, I don't really care about the surface. I only care about the boundary. It is important that we're taking the surface integral of the curl. So what is the curl? It's kind of like this idea related to rotation. And I'm going to try to give a bit of a gut feeling explanation for why this is maybe a sensible thing. Again, not a proof, but hopefully something that will help make a little bit of sense. So say I have a particular point on the surface, and kind of near that point, I have a curl that kind of goes this way. It, is going counterclockwise. For some little box, I have my curl is kind of suggesting a rotation that's going this direction. Well, near this little box on the surface, most of the time, if I'm not near a boundary, I have other little boxes that are next to it. So I have another little box here, maybe another little box over here, maybe another one over here, right? And again, if my field is kind of, continuously varying, I would expect that more or less for these small boxes that are pretty close to one another, they would have a pretty similar curl. But what I end up seeing is that at the interface between these interior boxes, where these edges line up, I kind of have, one curl kind of pointing one direction, the other one pointing the other direction. They, in a sense, cancel out. We saw this a bit more formally with Green's theorem, although still not completely formally. So all of these interior bits of the surface, where the surface is near other pieces of surface, these kind of curl bits seem to something like cancel out. But then if I interface with a box that's, say, near the boundary, and I'm going to use red for the boundary over here, I have a little chunk of boundary. Well, now again, I get, some cancellation here, some cancellation maybe with the boxes above or below. However, there's no match for this boundary curve going the other way. It's at the edge. There's no box kind of to the right of this one that kind of interfaces and provides some cancellation. So it seems like a lot of the stuff on the interior of the surface, everything has a matching edge to another box that seems like it's going to roughly cancel out, except at the boundary where I don't have a matching box next to it to provide that cancellation. So maybe that gives a bit of a gut feeling. Maybe that kind of resolves the paradox a little bit as to why we don't care much about the interior of the surface. The surface could be some complicated thing. It could be a super simple thing. But on the interior of the surface, we kind of have a lot of these little boxes right next to each other, providing lots of interior cancellation. And it's just at that boundary curve where we don't get that phenomenon happening, because at the boundary, that's kind of the meaning of the boundary, that there's nothing next to it on one side. Okay, so we're going to work through a proof of Stokes theorem in a special case. So for the special case where the surface is described by z equals g of xy. So I'd like to lay out a couple of bits of information to kind of start with here. So here we have some surface. And it has a boundary curve. Our surface is oriented upward, so its normals point up. It has a boundary curve that's oriented this way. That surface is g of xy for some domain in the xy plane with the usual xyz. And here we have a boundary curve. And we have a domain D. I'm going to call this boundary curve C. And I'm going to choose to call this boundary curve gamma because I was starting to run out of letters. So gamma the third letter in the Greek alphabet. Okay, so we have that z equals g of xy for xy in domain D. That's our surface. We'll suppose that we have a vector field that is PQR. PQ and R are scalar functions of three variables, x, y, and z. What else do we need? So gamma is the boundary of S, and C is the boundary of D. So our curve C, we can parameterize as R of t equals x of t comma y of t, that way. Our curve gamma we can parameterize as rho of t equals x of t comma y of t. The curve gamma is going to be directly above the curve C, but its height can vary, so it has the same x and y coordinates. And then it has a z coordinate g of x of t, y of t. And for both of these, t is in A and B. Now for my two-dimensional structures, my surface, I can parameterize by, say, sigma of u comma v equals u comma v comma g of uv. Note here that u and v can vary independently, whereas t can only, t is just t. So x of t and y of t are both linked by this common parameter t when we're in rho, the one-dimensional object. But here in the two-dimensional surface, u and v can vary independently. So even though these look similar, I'm trying to be careful with the details here. And then d is just described by the vector uv. And both of these, uv is in D. Okay, so I'm trying to lay out everything pretty carefully here because there are some nuances and some details that we're going to have to be careful with here. Probably not going to be able to fit everything on one or even a couple different screens here. All right, so let me actually bring Stokes' theorem down here, the conclusion. And let's investigate this conclusion of Stokes' theorem. So we see we have a left-hand side and a right-hand side. If I can show that the left-hand side equals something and then show the right-hand side equals that same thing, I will have shown Stokes' theorem. So here I have, on one hand, the integral over the boundary of S. I'm just going to write it this way. F dot dr. So the line integral over the closed curve boundary of S, or we're calling that gamma up here. And I can say that this is, well, F dot dr, or I suppose this is d rho actually, isn't it? D rho. Since I already kind of used R, I'm running out of letters to use here, but this is the integral over the boundary of S of p dx plus integral over the boundary of S q dy plus integral over the boundary of S r dz. So on one hand, that's what my left-hand side, I can rewrite it as that. And on the other hand, I can rewrite my right-hand side the surface integral of curl f dot ds. Well, the curl of f, well, f I could rewrite as pi hat plus qj hat plus r k hat. And the curl of the sum is the sum of the curls. That's a nice property of curl. And we see that this is the surface integral curl of pi hat ds plus the surface integral curl qj hat dot ds. There should be a dot d vector s plus the surface integral of curl rk hat dot ds. So I kind of, in my first line, I have kind of an x bit, a y bit, and a z bit related to dx, dy, and dz. And in my second line, I have kind of, again, an x, y, and z bit related to like I hat, j hat, and k hat. So in other words, if I can show that these two are equal to one another, if I can show that these two are equal to one another, and if I can show that these two are equal to one another, if I can show these three things independently, I'll have shown the whole right sides are equal to one another. And then, of course, I'll have shown Stokes theorem. So I'm going to call this bit A, this bit B, and this bit C. Now, one thing that I might notice here is that the roles of X and Y are more or less interchangeable, right? So the arguments to support A are going to be the same as those to support B. We just kind of swap variables. If we prove A, we just change P to Q, change X to Y, change I hat to J hat, more or less, and we essentially get the same argument gives me the same result. But note that C is different because Z is kind of fundamentally different than X and Y, right? It's the output of the function giving rise to the surface, where X and Y are the inputs. As a little bit of an aside, there's nothing super special about Z equals G of XY. The same argument would work for X equals G of Y and Z, or Y equals G of X and Z. We're just saying that we need to be able to make the surface one output variable in terms of a function of the other two input variables. But okay, so I'm going to prove A. This will essentially give me for free a proof of B, and then I'll prove C separately. So a proof of A and kind of for free, the proof of B goes as follows. So the line integral of the boundary of S of P dx, that's one piece that I'm interested in. If I can show that this equals something, and then I can separately investigate the surface integral of the curl of pi hat dot ds and show that equals the same thing, I'll have shown what I want to show for part A. So this is the left-hand side. Well, I can say that this is the integral from t equals a to b. Well, the boundary of S, that's gamma, that's x of t, y of t, g of x of t, y of t. So p is a function, this p of x, y, z, but then z is g of x, y, so that's why we have g of x of t, y of t here in the third component of p. And then we just have x prime of t dt. That's what dx turns out to be in the sense of an integral with respect to t. But I can re-envision this as a line integral over C, the boundary of D, the two-dimensional boundary up here in the xy plane. That's also a closed loop. And this would be P of x comma y comma g of xy dx. And this is kind of like the integral of p dx plus 0 dy. But this has the form of something I can use Green's theorem on. It's not a surprise that we're using Green's theorem here because we kind of said that Stokes is like a generalization of Green's theorem. We just kind of collapse the three-dimensional structure down to the two-dimensional structure so we can apply Green's theorem. So this is the double integral over the two-dimensional area D that's enclosed by that two-dimensional boundary curve C. And what is it? It would be what? Negative dq dx, but the q, so to speak, is just 0 in this case. Or I'm sorry, dq dx minus dp dy, but the q is just 0 in this case. So dq dx is 0 minus d dy of p of x comma y comma g of xy dA, where we're now dealing with a double integral in in actual two dimensions in the xy plane. And let's see what this integral turns out to be. That's negative the double integral over d. Now I need to take the partial with respect to y of p. I have to be a little bit careful here because p depends directly on x and directly on y, but it also depends indirectly on x and y through g. That's a g, not a y. So taking the partial of p with respect to y, on one hand, I just get the straight partial of p with respect to y. But then the other path takes me through g. I'm going to call this dp dz, the derivative of p with respect to its third variable. And I think I might have missed a parentheses here. Yeah, I think I did. The derivative of p with respect to its third variable is dp dz evaluated at x comma y comma g of xy times, in a sense, dz dy, but we're just going to call that dg dy. Z equals g of xy dA. So when I say dp dz, I mean the derivative of p with respect to its third variable evaluated at x comma y comma g of xy. So we're still in two variables here, x and y, but when I say z, I'm talking about the third input to p. Okay, so on one hand, our left-hand side equals this thing. It's not a super nice thing, but it is what it is. Can I make my right-hand side of A? Can I make this double integral of the curl, the surface integral of the curl, equal that same thing? So let's try. So my right-hand side, switching gears now to the other side. Well, what is this? This is the double integral of curl pi hat dot unit normal ds. It's that integral. And let's come off to the side here. We have that, what, r of u and v. I think this is what I call it r up here. Let me check my notes. Oh, I called it sigma of u and v now. So sigma of u and v is u comma v comma g of u v. That was my surface. The curl of pi hat, a short calculation shows that it's 0 comma dp dz comma negative dp dy. And what do I get from here? This is the double integral over d, our region in the xy plane, this domain D, of what? curl of pi hat dotted with negative gx, negative gy, comma, plus 1 dA. This was a formula we had seen before in the last section. Not necessarily with a curl, but just this transition here. And this is the double integral over d of, well, this is just, so curl of pi hat is this over here. This gives me negative dp dy from the z components, and then minus dp dz, dg dy. And that's integrated dA. But I notice that these two are indeed equal to one another. So therefore, we've shown the equality of these first terms, these first integrals. Again, since A and B are essentially the same thing, we get basically for free the proof of B as well. The proof of C is fundamentally different because, again, X and Y are kind of playing a symmetric role here, but Z is not. So Z is the odd one out, the one that can be written as a function of the other two to describe the surface. So we need to treat this one a bit differently. Okay, so let's take a look at C. So again, we're going to take the same approach. We're going to make our left-hand side equal something, make our right-hand side equal something, and then show that those two somethings are the same. So first, let's look at the line integral. Line integral over the boundary of S of R dz. Well, this is the integral t going from a to b of what? Of r times gx dx dt plus gy dy dt dt. Why this extra complication? Well, remember that z equals g of x, y. In other words, z of t is g of x of t comma y of t. So if we want to differentiate z with respect to t, we need to take the partial of g with respect to x times dx dt plus the partial of g with respect to y times dy dt. So using our chain rule there. And this is r times this. I'll put a dot there. It's not r dot that, it's just r times that, but I also don't want it to look like r of that or something. So r times this stuff in parentheses. But I can also think of this as the integral over the boundary of D, this two-dimensional boundary, this curve C, of what? Well, it would be like RGX. Let me write that a little better. RGX, comma, RdGdy, that vector dotted with a vector that looks like x prime of t dt, comma, y prime of t dt. But that's just what we're calling like dr. I hope that I have the right, is r the two-dimensional one? Yeah, that is dr. Okay. But this is the integral over the boundary of D of what? R dg dx dx plus r dg dy dy. This is like integral of p dx plus q dy for different p's and q's than the ones that we have above. But just reminiscing, just remembering that mnemonic, this is a candidate for Green's theorem. Again, as we'd expect, our Green's theorem is a little bit more complicated now because we have two terms in play. We have an x and a y term in play because we're dealing with z, which is a function of x and y. But by Green's theorem, this is the double integral over the interior of that two-dimensional domain D of what? The partial with respect to x of the thing on the dy bit. So r gy. Remember, r is a function of x, y, and z, and gy is a function of x and y. So r is like r of x comma y comma g of xy, and gy is like gy of x comma y. So I'm not writing all of the dependencies here because it's just a whole lot to write out, but I want to make that clear. Minus d dy of the stuff on the x, r times dg dx. That's all dA. Okay, so what do I need to do now? I need to be super careful with this. So r is r of x comma y comma g of xy. So r depends on, for instance, x in two different ways. One's directly and one is through the intermediate function g. And gy, for instance, is just gy of x comma y, just depending directly on x and y. Okay, so this first bit here, let me maybe do this part in blue. I have a product rule here. I have two functions that depend on x, r, and gy. So I need to use the product rule. So I differentiate r with respect to x. So that's what? dr dx, just the straight derivative with respect to x times the second, gy, plus dr dz, dz dx, or I'll just call it dg dx, times gy. Don't forget that second factor that still comes along. So the derivative of r with respect to x looks like rx plus rz gx. We've kind of seen that structure before in our previous bit up here, that same kind of structure. But we have an extra gy just kind of coming along for the ride now. That's the derivative of the first times the second, and then plus the first r times ddx of gy, but that's just gxy. We'll assume everything is nice enough that we can switch the partials with no problem. And then minus, might actually need to move these guys out of the way a little bit. Now we got to do the same thing for ddy r gx, and it's going to be very similar. So dr dy, the direct dependence of r on y, times dg dx, just coming along for the ride, plus, well, the indirect dependence on y of r. So let's say that's a plus, not a t. So we have dr dz with derivative with respect to its third component times dg dy. And again, we have a gx factor coming along for the ride. That was the derivative of r with respect to y times gx plus r derivative of gx with respect to y. It's going to be very similar to this one, just a direct dependence. dg dx with respect to y is gxy. All of this dA. Nicely enough, I get massive cancellation here. rgxy goes away. rz gx times gy goes away. And I'm left simply with, maybe not so simply, but double integral over d of rx gy minus ry gx dA. One thing that I think is a little bit funny about this is that if you completely forgot about the chain rule, if you just, if it just slipped your mind or something and you said, how do I do these derivatives? If you forgot about the chain rule and kind of forgot about the product rule, you might have mistakenly just differentiated r with respect to x, then differentiated r with respect to y and written that down. And that's, you would have actually got the right answer for the wrong reason. So you need to expand it all out, get a whole bunch of terms, but then a whole bunch of stuff cancels. And I don't know, it's a little bit funny that it's almost like that, 16 over 64, you can cancel the sixes and get 1/4 kind of idea that like, you know, happens to work just by chance. Anyway, so that's what our left-hand side turned out to be. Can we make the right-hand side look like the same thing? What was the right-hand side? The surface integral of the curl of rk dot ds. Okay, so let's investigate this. Well, this turns into the double integral over domain D of ry comma negative rx comma 0 dotted with negative dg dx, negative dg dy, comma 1 dA. Similar idea as we had up here. But this just turns out to be the double integral over d of, if I do this dot product, I get, well, negative from the well, the last term zeroes out. From the middle term, I get negative rx times negative gy. That's just rx gy. And then from the first terms, I get negative ry gx dA. Well, that was a heck of a lot easier to do than the last bit, thankfully. And I see that these are equal. I've now shown A, which effectively shows B. I've shown C. I've shown each of these terms are equal to one another. So these two right-hand sides are equal to one another. So I've proven Stokes' theorem in the case where my surface is z equals g of xy, where it can be described that way. Okay, let's look at an example. Here we're going to verify Stokes' theorem. So we're going to compute the left-hand side, we're going to compute the right-hand side and show that the two are equal. And we're going to do it for we're going to end up doing 3 integrals. We're going to verify it for a specific field for 2 different surfaces. So I'm going to compute 2 surface integrals and 1 line integral, and hopefully we'll show that they're all equal to the same value. This will kind of demonstrate or verify Stokes' theorem, as well as kind of demonstrating or verifying the idea of surface independence. Of course, this isn't a proof, right? But this is just a demonstration of their equality. Okay, so let's start with, well, I suppose let's start at the very beginning with what Stokes' theorem says. So let's again copy it down, just as a reminder, so that we know what integrals we have to compute. Let's start by computing the line integral. So I want to compute the integral over the closed curve f dot dr. All right, so both of these surfaces, very important that both of these surfaces have the same boundary curve. The disk of radius 1 in the xy plane has the boundary curve that is just the circle of radius 1 in the xy plane. And the upper half hemisphere of radius 1 has that same boundary curve. So my good old circle of radius 1 in the xy plane, that is the curve that I'm dealing with. Now my curve really is technically embedded in 3 dimensions, but it's always in the xy plane, so my z component is just always 0. And then I'll use the same mode parameterization, x equals cos t, y equals sine t, letting t go between 0 and 2 pi. That should do the trick of tracing out this curve. I need dr, so I'm going to need x prime of t, negative sine t, y prime of t, cos t, and z prime of t, of course, is also 0. So what's my line integral? That's the integral of t going from 0 to 2 pi of, well, I just need f dot dr. So I need z. Well, let me write that out. So I need z, but z is 0, comma x is cos t, comma negative x, negative cos t. So that's what f is in terms of the parameterization. This is f. And then dot dr, but that's dot r prime dt. Negative sine t, cos t, 0, dt. Our first and third components both have a 0 contribution, so we just end up with integral t equals 0 to 2 pi of what? Cos squared t dt. And this integral turns out to be pi. So that's what my line integral ends up being. What about my surface integral for the surface A, for the disk of radius 1 in the xy plane? Just kind of the simplest surface that we can get that has this as its boundary curve. So here is my surface. And I want to compute the surface integral of what? Of the curl of f dot ds. Well, let's come up here and compute the curl of f. So what's the curl of f? That's the determinant of I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, and f is z, comma x, comma minus x. So this is I times partial of y with respect to, or partial with respect to y of minus x is 0. And then I times partial with respect to z of x is 0. So no contribution for the I component. J times partial with respect to z of z is 1, minus j times partial with respect to x of minus x is minus 1. And for our k component, we have k times partial with respect to x of x is 1, minus k times partial with respect to y of z is 0. So my curl is 0, 2, 1. Okay, so what do I have here? Well, this is the double integral over our domain D, this flat surface, of the curl of f, 0, 2, 1, dotted with, well, what's my unit normal to the surface, that's just k, that's just 0, 0, 1 dA. But this is just the double integral over this domain of 1 dA. That's just the area of this circle of radius 1. That's just pi. So I verified Stokes' theorem for this surface, this disk of radius 1. I've shown that the surface integral over that disk of this field equals the line integral. The surface integral over the disk of the curl of the field, I should say, equals that line integral. So that was a pretty easy calculation to do, mainly because the surface was nice and flat, and we could find its area really easily. Now, what about part B, a more challenging surface integral? We have the upper half hemisphere that we're working with here. So let's take a look at this one. So I have my upper half hemisphere, that's my surface. I want my normals pointing upwards. And I want my boundary curve, I suppose, pointing that way. So let's try to figure out this surface integral. Over this surface. Okay, well, we have a formula for this. This is the double integral over domain D of, and let's say that curl F equals P comma Q comma R. So these are the components of the curl of F, not of F itself. Negative P gx minus Q dg dy plus R dA. So again, that was a formula coming out of the surface integral section. And we know that the curl of F is 0 to 1. So P is 0, Q is 2, R is 1. So I need to figure out what's dg dy. Well, this upper half hemisphere with Z being positive, I can write as Z equals root 1 minus x squared minus y squared. And dg dy is 1 over root 1 minus x squared minus y squared times negative y. We could call it, we could describe it this way, or we could say it's negative y over z if we wanted to. But this is the double integral over d of, well, P was 0 for this particular field. So the curl of F has 0 in that first component. So I get no contribution from here. Minus Q, so minus 2 dg dy, but that's just a 2y over root 1 minus x squared minus y squared. I'm going to write all of this out because I'm trying to be cognizant of the fact that I am in a double integral here dA, so I'll try to only have x's and y's floating around. And then just the regular old plus r, or just plus 1 dA. All right, that just comes from that third component of the curl. I see that this is the integral of the sum of two integrands, And the second one just contributes double integral of d dA, just the area of this region, the area of the circle of radius 1 is pi. So we get a plus pi coming from that plus 1 here. And then I have this double integral of 2y over root 1 minus x squared minus y squared. I guess what I could do here is use maybe polar coordinates. I can make this 2r sine theta over root 1 minus r squared dr d theta. Theta is going from 0 to 2 pi. R is going from 0 to 1. I notice that my integrand is function of theta times function of r. So this integral over theta sine theta can all come out. But that gives me integral theta equals 0 to 2 pi of sine theta d theta. That's just the big 0 times whatever the integral in r is. I can look at the integral in r and I can see that it's not going to blow up or something. So even though it is maybe a little bit sketchy with this seeming like we're about to divide by 0, but we can do a simple substitution and see that that's not going to be a problem. But the theta integral brings out a factor of 0, which just zeroes out this entire integral. And we're left with simply pi as the answer. The same as the line integral. So again, verifying Stokes for a different surface, and the same as the previous surface. So demonstrating that surface independence. Okay, so let's take a look at a few applications of Stokes' theorem. So we'll see in the divergence theorem section that divergence is a bit like outward flux per unit volume. And, or perhaps it is outward flux per unit volume in a sense. Curl is kind of like circulation per unit area. So we're going all the way back to when we defined divergence and curl, and then we're revisiting them and talking about what they mean, but in a little bit more of a mathematically precise way. And remember, when we introduced the idea of curl, we kind of said if I have a two-dimensional vector field, I think of putting like a little paddle wheel in there and seeing, what direction would it tend to spin. If it tends to spin counterclockwise, I say the curl is positive, and clockwise, I say the curl is negative. And if it tends not to spin at all, then the curl is 0. So again, we had this kind of gut feeling, then we looked at a couple of vector fields and compared them with the definition of curl and saw that that was, I suppose, a sensible intuition. Can we add some meat to that? Can we really show that that's actually true and it wasn't just that we happen to choose vector fields that happen to make it look that way? Okay, so suppose we have the line integral of over a closed curve of f dot dr. In Green's theorem, we had a name for this. We called it the circulation. Again, we can kind of think of this being like integral of f dot unit tangent vector dt. So it's kind of like the tangential component of the field going around this curve. So if I have some curve, and if my field is kind of tending to kind of go along with the curve, I would expect, this is called a circulation because it kind of feels like we're like circling around something, like we're creating a vortex or something like that. So this is called the circulation. And by Stokes' theorem, this is the double integral over S of curl of f dot ds, but I can say that that's dot n hat d regular s. But if I consider a really small surface, so if I have some big three-dimensional surface, this is some big surface integral, but if I take just a really small chunk of surface, well, the curl of f is a nice continuous field. It shouldn't change that much over that surface. So this is approximately double integral over f. This is for small s, for a surface whose area has a small area. Curl of f evaluated at a point p naught So say the curl of f at this point dot n ds. But also the normal over this small chunk of surface, that should also be a constant. I suppose if I really wanted to, I could call this something like n at p naught as well. But this is basically just the double integral of a constant ds, the surface integral of a constant. But that's just like curl of f at p naught dot the normal there. So that result times the area. So if I imagine I have a little chunk of surface here, and I have some normal, I also know that curl f dot n is like length curl f at p naught times length of the normal, but that's a unit normal. It just has length 1, so we can just get rid of that. So times the area. Whoops, I forgot an important piece. The dot product is length times cos theta, very important, times area of S. Remember, the curl is orthogonal to kind of the rotational direction. So what am I saying here? If the curl of F at P naught is kind of close to parallel with the normal at P naught, if the angle between them is small, well, for small theta, cos theta is close to 1. And the length of the curl of F is like circulation per unit area. It's like circulation over area. So if my kind of tendency to rotate is in a sense, if I'm in a sense rotating within the surface or kind of within a tangent plane to the surface, then my curl F is going to be pretty close to parallel with the normal. And I get this idea that curl F is like the circulation per unit area. Now, if my tendency to rotate was either non-existent, or maybe if it was, oops, again, OneNote trying to be a little too helpful here. If it was either tending not to rotate at all around here, or if the rotation was like kind of like perpendicular or something to my surface, to my normal to my surface, well, then my curl and my normal to the surface are going to be close to perpendicular. My cosine is going to be near 0. And then my circulation is close to 0. But if my rotational tendency is kind of in the same plane, so to speak, as the surface, or is in the same plane or a similar plane to the tangent plane to the surface, in that case, curl looks like circulation per unit area. So curl is a bit like maybe circulation per unit area that is in the tangent plane to the surface. So that's why I say it's a bit like circulation per unit area. Okay, another application of Stokes' theorem. Well, we had this theorem we discussed previously that f is conservative if and only if curl f equals 0. So if f is conservative, then curl f equals 0. And if curl f is 0, then f is conservative. Going this way, we showed that before. We showed that if f is conservative, then curl f is 0. That came from our combining together div, grad, and curl in different ways, and we showed that pretty straightforwardly. But we didn't actually show this. We didn't show that if curl f is 0, then f is conservative. But this is actually pretty easy to show with Stokes' theorem. So let's assume that curl f is 0. And this should be the 0 vector. So we'll fix that. So assume curl f is 0. Then what do I have? Well, the line integral around a closed curve, f dot dr, well, by Stokes, that's the surface integral of the curl of f dot ds, but curl of f is the 0 vector. So that surface integral is just always 0. But there's nothing special about, I didn't choose a specific closed curve. This is really true for any closed curve. So for any closed curve C, the line integral over that closed curve of f dot dr is 0. If the curl of f is 0. So this is by Stokes' theorem that we showed this. But remember that when we talked about conservative vector fields, we had a few different characterizations, a few different equivalent ways of saying that same thing. And the line integral over a closed curve being 0, not just for one or two closed curves, but for any closed curve, that was a characterization of a conservative vector field. So therefore, f is conservative. So this is quite simple to prove after we have Stokes' theorem. And then a third example, Faraday's law of induction, one of Maxwell's equations. So Faraday's law in integral form states the following. We're going to try to convert it to differential form. So this is a so-called law of nature. It's somebody came up with this idea. They did a bunch of experiments. They tried to disprove it. They weren't able to disprove it, at least not under reasonable conditions. And so therefore it's a law of physics. So we're not saying that we proved this, and we're not going to attempt to somehow like prove this mathematically, this equation. We're saying that some physicist somewhere says this is a law of nature. What we're going to do is we're going to try to rephrase this to, instead of being an integral relationship, to being a differential relationship. So we'd like to get the differential form of Faraday's law. Maybe for whatever application we're working with, that's the easier version to use than this one. So what does this say? This says the line integral over a closed curve of the electric field, E. Here we're thinking of these fields as being functions of space as well as time. They can vary in time as well. That's negative. Well, this is the surface integral, the integral over a surface of the magnetic field. Now, a surface integral is going to integrate over space, over x, y, z, but not over t. So this surface integral, once completed, will still be a function of t. And then we take negative d dt of that function of t. Okay, so, and importantly, c is the boundary of S here. So we would like to reframe this in terms of derivatives instead of integrals. How can we do that? Well, we can look at the left-hand side integral over C of E dot dr. This should be dot there. So that's the left-hand side. We can rewrite that by Stokes' theorem as the double integral over the surface. Remember that C is the boundary of the surface S of the curl, which I'll choose to write this way. Grad cross E dot N ds. So on one hand, that's what the line integral equals. On the other hand, by Faraday's law, the line integral equals negative d by dt of this, the magnetic field dotted with N ds. As long as I have nice continuous partials and so on, I can move this. Remember, this surface integral is an integral in x, y, and z, but not t. This d by dt can just kind of come inside and hit that b. So this is just the surface integral of the partial of b with respect to t with a negative sign dot n ds. We have a partial now because outside of the double integral, all of this, the spatial variables are integrated away. We're just left with a function of t. But on the inside, my magnetic field is still a function of x, y, z, and t. So we need to take the partial here. But all of this tells me, keep in mind that this is true for any curve and any surface where that curve is the boundary of the surface, not just for some specific surface. So the integrands then must be equal. So that tells me that the curl of the electric field is negative the time rate of change of the magnetic field. And this is the differential form of Faraday's law. It's the same physical principle, just written in a different way. And sometimes it might be better to think of it one way, other times it might be better to think of it another way. Okay, and then the last bit here, we'll go back to something more practical. We'll go back to an example. Here we have example 2. Let C be the triangle going between these different points. So let's draw it out. So going from 3, 0, 0 to 0, 3, 0 to 0, 0, 6, and then back to 3, 0, 0. So this oriented curve is the curve C. And we have enclosed here a triangle. This is oriented upwards, so the normal has a positive z component. And we want to integrate the line integral of f dot dr. We have some field here that we're dealing with. We want to compute this line integral. Now, one way to compute this line integral would be to say, make this curve C1, C2, C3, parameterize each of them separately, do a line integral over each curve, being really careful that we get the direction correct for each of them, and then add them together. We could do that. That would be a decent bit of work, not a tremendous amount of work. And in fact, I'll leave it as an exercise to do just that. It might be a good review of line integrals. And just kind of as an aside, C1, the line integral should be 9. C2, it should be -9, and C3, you should get -9. So those should be the values of those three line integrals. So when we add them all together, we should end up with a sum of -9. But is there maybe an easier way to do this? Well, yeah, maybe we could use Stokes' theorem. So by Stokes' theorem, this is the surface integral of curl F dot n ds. And again, from a theorem and or formula in section 7, this is the double integral over this domain D. What haven't I used yet? Blue, I guess. The domain D in the xy plane. So this is the double integral over D of the vector I'm interested in, which happens to be curl F here, dotted with -gx, -gy, comma, +1. So we are oriented upward, dA. Where g of xy, z equals g of xy, is the description of my surface. Okay, so I need a couple of pieces to plug in here. Curl of F is ijk, the x partial, y and z partials, and -y², z, and x. So again, we have I times the y partial of x minus, that's 0, and then minus I times the z partial of z is -1, plus j times the z partial of -y² is 0, minus the x partial of x is -1 as well. And then k, I have the x partial of z is 0, minus the y partial of -y² is -2y. So minus a -2y, that gives me a +2y. Or my curl is -1, -1, 2y. And then the question is, what's a formula for this plane? And there's a few different ways you could go about this, either finding a formula for the plane or the normal for the plane. But a formula for the plane is 2x plus 2y plus z equals 6. And then, of course, negative dg dx. So here we have z equals g of x comma y is 6 minus 2x minus 2y. So negative dg dx is -2 is 2, negative dg dy is 2, and then 1 from up above. Or we could just pull out the normal directly from the equation, however you want to go about it. dA. Okay, so if I do this dot product, I get -2 plus 2y. So I think I get 2y minus 4. And then what does my region of integration look like? This is x plus y equals 3. And here I see I have an integrand with y in it. I think it'll be slightly easier to integrate with x on the inside. So I'll let x go from 0 to 3 minus y. and then I'll let y go from 0 to 3. So when I integrate with respect to x, I just get a factor of 3 minus y coming down. I multiply all of that out, simplify, integrate that y from going from 0 to 3, and I end up with just minus 9, as I would have expected from the solution to the exercise that I gave you up here. Okay, so that finishes up our discussion on Stokes Theorem 16.8. Hopefully gives you some insight into both some applications in physics and engineering where this is actually useful, and some practical examples of how it can be useful. In particular, note that, strategically, if I had asked something like the question in part B of example 1, you could use Stokes theorem to say change it into the question in part A of example 1 and save yourself, a whole lot of work, right, and a lot of hassle. So some practical applications and some applications to other fields.